All right, using the tools that we now have with conditional expectation, conditional variance is good. It makes our lives much easier now for calculating expectation and variance of a random sum. Okay, so what do I mean by this? So we've previously talked about the case where we're interested in the random variable S sub n, which is defined as the sum from I equals 1 to capital N of X sub I, where capital N is a random variable. Okay, so for X1, X2, independent of each other, well, for N, X1, X1, X2, etc., independent, expectation of xi equal to mu for all I, variance of xi equal to sigma square for all I, and n a non-negative integer valued random variable. What is the expectation and variance of S sub n? Well, the expectation of S sub n, we can easily do now as it's the expectation by the Tower property of the conditional expectation of S sub n given n. Okay. But given n, the expectation of S sub n is n times the expectation of x1. Expectation of x1 is mu times the expectation of n. So this is just expectation of n times expectation of x1. So we've already calculated that in a prior class, but it took many more steps because we had to work directly from the distribution. We had to have a little bit of a trick to change the limits of integration so that it didn't depend on the random variable. And then we changed the order of the integration, and that's where we end up getting the answer. But here with the techniques we now have for conditional expectation, we're in much better shape. Okay, so how do we show this now? Variance of Sn. Well, we want to show that variance of Sn is equal to expectation of x1 quantity squared times the variance of n plus the expectation of n times the variance of x. Well, the variance of Sn given that n is equal to a particular value, little n. Well, this is the variance of Sn, S little n, which is n times sigma squared. So then in particular, this tells us that the variance of Sn given n is n capital N times sigma squared. And the expectation of Sn, we already calculated before. We know that that's expectation of n times the expectation times mu. So then the variance of the expectation, conditional expectation of Sn given n, well, this is the variance of n sigma squared. This is sigma. This is the variance of, sorry, expectation of Sn given n. The variance of n times the expectation of x, which is expectation of x squared times the variance of n. So what we're left with is variance of Sn, as we know, is equal to variance of the conditional expectation of Sn given n plus expectation, going by the ANOVA formula, of the conditional variance of y given, of Sn given. So this is equal to expectation of x squared, variance of n plus expectation of the variance is expectation of n times the variance of x1. So note that a few things. First, the expectation of the conditional expectation of y given x is the expectation of y. Second is that variance of y is variance of expectation of y given x plus expectation of variance of y. Okay. How do we show that? Well, the way that we show that is variance of y is expectation of y squared minus the square of the expectation. This is, by the Tower property, expectation of the conditional expectation of y squared given x. Use the Tower property twice. Now we are going to copy this down. And we're going to subtract off expectation of y given x squared plus expectation of expectation of y given x squared minus expectation of the conditional expectation squared. This, by definition, is the expectation of the variance, the conditional variance. And this is the variance of the conditional expectation. So now for a dice example, let's see how we can apply this to another situation. So let's suppose we have a 10-sided die. And if we roll a 1 up through a 7, we win that many dollars. And we start over. Meaning we roll again. And we would continue to win that many dollars. If we roll an 8, 9, or 10, we win that many dollars and quit. Okay. So what's the expectation and variance? Number of rolls N is going to be the number of rolls needed. Number of rolls in the game. W is going to be the amount won. So we're going to toss a coin. So this is the equivalent to tossing a coin with success probability. Three-tenths. So if we toss success, meaning head probability. So if we toss a tail, which we're defining as a 1 up through 7, right? We get a random number that's uniform from 1 to 7. And if we toss a head, we get a random number which is uniform on the set 8, 9, 10, but then we stop, right? So number of tails before the first head. So length of the game is number of tosses until first head, which is geometric with success 3/10. And the number of dollars won. Well, let's do this number of tails. Okay. And the number of dollars won, W, is V plus Sn, where S sub n is the sum of U1 up through UN of these UIs that are uniform from 1 to 7. Right? So then in this case, we know that the expectation of N, which in this parameterization is the number of tails before the first head, so it's Q over P. Right, which is 7/3. The expected value of U1 is the expected value. It's the midpoint between 1 and 7, right? So it's 1 plus 7 divided by 2, which is 4. The expectation of V is the midpoint between 8, 9, and 10, which is 9. Calculated as 8 plus 10 divided by 2, which is 9. The variance of N is geometric. It's Q over P squared. 7 over 9. Sorry. 70 over 9. The variance of U1 is 7 squared minus 1 over 12, so that's 4. And the variance of U2, we can calculate that directly, it's 2/3. Okay, so what is the expectation of the amount we win? Right, the expected value of W is the expected value of V plus Sn, which is expected value of V plus expected value of N times the expected value of U1. Okay, so this is just putting all the pieces together. So it's 9 plus 7/3 times 4. 55 over 3. And the variance, which is the variance of V plus Sn. Well, V and Sn are independent, so it's the variance of V plus the variance of Sn. And now we can just use the formula we already know, right? The variance of V, which we've calculated to be, oh, I'm sorry, this should be the variance of V, not variance of U2. Variance of V is 2/3 plus, we need now the expectation of U1 squared as the variance of N plus the variance of U1 times the expectation of N, which is 2/3 4 squared times 70 over 9 plus 4 times 7 over 3. It's 134 4/9. So this is an application of a situation that at first might look a little bit confusing, might look a little bit complex. We have different values that we get depending on different roles, but what we can easily see then is that when we break it down in terms of the behaviors of the random variables and we use the properties that we've already developed, everything's tractable. We just have to take everything step by step.